بسم الله الرحمن الرحيم. محاضرة اليوم بتتكلم عن بعض الثيورمز المفيدة في DFT اللي هو Discrete Fourier Transform. So this is our title, some useful theorems of the DFT. Okay, so let's take, to start our discussion, let's take the two examples, x of n, which has the DFT of x of k, and h of n, which has the DFT of h of k. So basically we have those two. Now we'll start with the theorems. Theorem number one is linearity. So linearity mainly is applicable because of the definition of the DFT. So linearity means that if we have certain or linear combination of x of n and h of n, then also we have a linear combination of their DFTs, the same linear combination of their DFTs. Alpha x of n plus beta h of n has the DFT of alpha x of k plus beta h of k. So this is theorem number one, and it's really helpful. But we don't have to demonstrate that by an example. It's really something very simple. Okay, so the second theorem is the circular time shifting. Circular time shifting, if we have a circular shift of a sequence, x of n minus n0 modulo n, this is a circular shift of the sequence, x of n. This has the DFT of w sub n to the power n0 times k times x of k. Okay? So maybe it's really nice here to have an example. Let's take the following example here as x of n equals to the sequence 1, 2, 3, and 4. So we have a sequence of 4 elements. N is equal to 4. If we define y of n, which is equal to x of n minus 2 modulo 4, this is equal to 3, 4, 1, and 2. This has been demonstrated previously in previous session. So what we need to find here, find y of k. So the first method to find y of k is to apply directly from the definition of the Fourier transform. So y of k is equal to d4 times y of n, which is equal to 1, 1, 1, 1, 1, 1, 1. This is minus j, minus 1, j, minus 1, 1, minus 1, j, minus 1, and minus j. This should be multiplied by 3, 4, 1, and 2. And if we multiply those, we end up with the first row times the column, give us 3 plus 4 plus 1 plus 2. the second row times the column is equal to 3 minus j4 minus 1 plus j2. The third row times the column is equal to 3 minus 4 plus 1 minus 2. And the last row is 3 plus j4 minus 1 minus j2. And the end result is equal to the vector of 10, 2 minus j2 minus 2, 2 plus j2. So this is the final answer of the circular time shifting. If you do this, we do it in time domain and find the DFT in the normal manner. We can make use of the theorem. So if we make use of the theorem using the circular time shifting theorem, circular time shifting theorem, y of k is equal to w sub 4 to the power 2k times x of k. Okay. So, knowing that x of k is equal to d4 so this is d4 times x of n which is 1, 2, 3, and 4, and we get x of k to be equal to 10 minus 2 plus j2 minus 2 minus 2 minus j2. So this is x of k. Taking this here, so this will be equal to y of k is equal to w sub 4 to the power 0, w sub 4 to the power 2, w sub 4 to the power 4, and w sub 4 to the power 6. This is point by point multiplication with 10 minus 2 plus j2 minus 2 minus 2 minus j2. So this is equals to w4 to the power 0 is 1, w4 to the power 2 is j, sorry, this is minus 1, w4 to the power 4 is, okay, w4 to the power 4 is also 1, and w4 to the power 6 is minus 1. So this is point by point multiplication with 10 minus 2 plus j2 minus 2 minus 2 minus j2. And the end result of y of k is equal to 10 okay, minus, it's 2 minus j2 minus 2 and 2 plus j2. And it is supposed to be exactly the same answer that we got in the time domain. Okay, so both answers are the same. This is the same as in the previous solution. Okay, so we demonstrated the the circular time shifting.